Hey everybody, welcome to our lesson video for section 8.3. We're going to continue learning how to graph quadratic functions in this section. And just like we've been doing in 8.2 as well, we're just going to keep adding in pieces to the quadratic equation so that we can graph increasingly complex quadratic functions. So for today's video, obviously you'll want to use graph paper because we're graphing. And you'll want to start by setting it up with the section, the date, and the I can statement, and then resume the video as soon as you've done that. All right, so we're actually going to start with one of our core concepts for today, and part of this is review and part of it is new. So I want you to take a look at the function on the right side, and you might want to sketch this picture in your notes as well. Our goal today is to be able to graph a quadratic function of the form ax squared plus bx plus c. If you notice, 2/3 of this look familiar because we already did ax squared plus c in 8.2. So we're just adding in the middle bx term today. So two of these things we can already kind of figure out. For example, what does the a value tell us? Well, we already looked at this. If the a value is positive, then we know that the parabola, or the U shape, is going to open upward. And if A is negative, we know that it's going to open downward. And we also talked about that you can use that A value as sort of a pseudo-slope for the first point on either side of the vertex in order to get two additional points. Now, we also know the y-intercept as well. We saw this in 8.2 because C represents a vertical shift up and down for the y-intercept. So in other words, the y-intercept will be at the point 0, C. So if we plug in 0 for all the x's, we would be just left with C on the right side of the equation, which would give us our y-intercept. So now we have two new pieces of information because the bx term allows us to shift the parabola left and right. But what you'll notice here is the shift is not just the b value. And that's important because that's often a mistake that students make. It's a little bit more complicated than that. So the axis of symmetry, which is this dashed line that goes through the vertex and represents the symmetry point of the parabola, there's an equation that we can use to find the axis of symmetry. And this equation is one that, for now, I'm just going to give you. Later on this year, when we learn a little bit more about the algebra for quadratic functions, you're going to see exactly where this equation comes from. So the equation for the axis of symmetry, if you notice, it's a vertical line, so it's going to be x equals, and the equation is x equals negative b over 2a, where the b and a come from the original quadratic function. So the axis of symmetry, if you look at the picture, you'll notice it goes through the vertex, which means the vertex has to be a point where the axis of symmetry point is the x-coordinate of the vertex. And then to find the y-coordinate of the vertex, all we're going to do is plug in x to find y. We're going to plug in the x-coordinate back into the original function, and that'll give us the y-coordinate for the vertex. So with this information, we'll now be able to graph these types of quadratic functions. So let's take a look at this so you can see an example. So imagine we wanted to graph f of x equals 3x squared minus 6x plus 5 and determine the domain and the range. We're going to go through the 4 steps to do this, and you'll see what this will look like. So for step 1, we need to find the axis of symmetry first. And to do that, we're going to use our equation x equals negative b over 2a. And in this case, b is negative 6, a is 3, and c is 5. So negative b over 2a would be negative 6 over 2 times 3. In other words, it's 6 over 6, which equals 1. So I'm going to draw in our axis of symmetry along the line x equals 1. So then step 2, we want to find the vertex. And to find the vertex, we already know the x-coordinate because the x-coordinate is just going to be 1. So we're going to plug 1 in for x to find f of 1. And when we simplify that, we have 3 times 1 minus 6, which is negative 3, plus 5 is 2. So our vertex is going to be at 1, 2. So I'll put that on my graph as well. So then for step 3, we're going to plot our y-intercept and a symmetrical point. So now the y-intercept is just the c value. So since c equals 5, our y-intercept is 0, 5. So I'm going to go up to 5, plot a point, plot its symmetrical point across the axis of symmetry as well. And then step 4, all we need to do is graph. So I will draw in my points, making sure to include arrows. Now one thing you'll notice here is once you have the vertex, if you wanted to, you could also get the next 2 points by using the a value and going 1 point to the right and 1 point to the left, because the a value in this case is 3, so we would go up 3 over 1 to the right, up 3 over 1 to the left. So in terms of domain and range here, because it opens upwards and outwards forever, our domain is negative infinity is less than x, which is less than infinity. Our range, the bottom point here is 2. So we would be at 2 is less than or equal to y, which is less than infinity. So this is an example of how you graph quadratic functions that include a bx term. So our next core concept here, we just need to talk for a moment about some vocabulary that might actually seem fairly intuitive. Basically, we want to talk about maximum and minimum values because a lot of real-world situations require you to find a maximum or a minimum to something that's moving parabolically. In other words, something that's modeled by a quadratic function. And the key here really is that if you have a positive or a negative a value, so you're opening downwards, then your vertex is also your maximum. Whereas if you have a positive a value, then your vertex is at the bottom of your parabola, so it represents a minimum. So if you're doing your homework and you're looking at a word problem and it asks you to find a maximum, I want you to think in your head, oh, okay, that means I want to find the vertex. And similarly, if they ask you to find a minimum, you're going to think to yourself, okay, they want me to find the vertex. So let's look at an example of this both by hand and on a calculator. So in Michigan, there is an extremely long bridge that crosses Lake Superior. And there is a suspension cable that runs to support the bridge. And that suspension cable is parabolic. And in fact, it can be modeled by the equation shown. You'll notice that it has an extremely small a value because it's extremely vertically compressed. It's very wide, not very tall, as you would guess from a bridge. So in this case, x and y are measured in feet for this problem. So we want to know the height of the cable above the water at its lowest point. In other words, we want to know the minimum height, which really means we want to find the vertex. So to do that, we need to find the x and y coordinates of the vertex. So we're going to start here by using x equals negative b over 2a to find out the x coordinate of that vertex. So negative b over 2a, if we look up here, so that would be negative 0.37 divided by 2 times 0.00098. And if you put this into your calculator, you should end up with 1,887.76 feet. And that makes sense because if you look at the picture, you'll notice that the minimum occurs between 1,500 and 2,000. So now, if we want to find the height of the cable above the water at its lowest point, which is what the problem was actually asking for, that's really asking for the y-coordinate of the vertex. So we're going to take that x-coordinate and we're going to plug it back into our original equation. So we have 0.000098 multiplied by 1,887.76 squared minus 0.37 times 1,887.76 plus 552. So you can plug this entire thing into your calculator in one long string. You should end up with about 202.77 feet. So that would be the minimum height that the bridge is above the water. So now, one thing I want to show you guys before we wrap this video up is that you can do this on your calculator as well. So if I open up a calculator app here, if we type this function into y equals, we can actually graph it. So we have 0.000098 x squared minus 0.37x plus 552. So now obviously if I go to graph this right now, I'm not going to see anything, right? Because if you look at this problem, the graph actually gives us our window for us. In this case, we need a much larger window for this bridge, which makes total sense. So for x, I'm going to go from -10 to 4,000. And for y, I'm going to go from, I don't know, -50 to 550. So now if I hit graph here, I probably should have gone even higher just to make it look less extreme here. But as long as I can see the whole parabola, I can now use a feature of the calculator to find the minimum. And to do that, we're going to press the second button and then trace. And above trace, you'll see the word calculate. And we can choose things to calculate. And in this case, we want to calculate the minimum value. So I go down to minimum and hit enter. And it's going to ask you 3 questions. The first question is left bound. And what it wants you to do is scroll to the left of the minimum. You're kind of telling the calculator approximately where the minimum is. So we would go left bound and hit enter. And then we'll go to right bound and hit enter. And you'll notice that it brackets it for you. So that's the only place the calculator is going to look for the minimum. And then to help it out, it wants you to move close and then hit enter one more time to guess. And then it'll tell you exactly what the minimum is. And you can see here that our minimum matches up nicely with what we calculated algebraically as well. So this is just another way to use your calculator to help you find minimum and maximum values, particularly when your quadratic function is very complicated. So that brings us to the end of our 8.3 lesson video. Make sure you use graph paper for the homework and let me know if you have questions.